This paper is about time and communication efficient overlay network construction via gossip. I'm Gopal Pandurangan. This is joint work with Fabien Dufoulon, Michael Moorman, and William K. Moses Jr. Many of today's large-scale distributed systems in the internet are P2P or overlay networks. P2P connections in P2P networks are formed within nodes, and these connections are actually virtual connections that overlay on top of the actual physical internet. And a node can communicate with another node if it knows the IP address of the node. And if a node knows the IP address, it can establish a connection to it. Thus, unlike generally static networks, peer-to-peer networks are reconfigurable. That means a node can add new connections to other nodes whose identifier it knows. Identifier in this case is basically the IP address, or it can drop existing connections. And this is the P2P model that we are going to use in this talk. So this work is focused on the so-called overlay network construction problem, which has been very well studied, especially in the context of peer-to-peer and overlay networks. And in this problem, we are given an arbitrary reconfigurable network, and the goal is to reconfigure it. That means change the topology so that it becomes a bounded degree, rather a constant degree expander graph. As you know, expander networks are graphs which have constant conductance. And just to recall, conductance of a subset S is simply the ratio of the number of edges leaving the subset to the volume of the subset, the minimum of the volume of the subset and the volume of the complement subset. And for expander graphs, this conductance is constant for every subset. And the goal of the problem is to design distributed algorithms that are efficient. That means we want small number of rounds fast, and we also want small communication cost. That means very small message complexity. And the reason why overlay construction problem is concerned with expanders is that expander networks, as very well known for many years, is that they have very desirable properties such as low diameter, high conductance, robustness to adversarial deletions, etc., which are crucial to the performance of real-world networks, in particular P2P networks. And in fact, real-world P2P networks such as Bitcoin, they try to build a random graph topology, and the idea is random graphs are expanders with high probability, and thus they have these desirable properties. So let's look at prior work. So we are assuming a connected reconfigured graph on n nodes and m edges. This is the initial graph. So one of the earliest works to deal with this problem is by Angolin, Aspinus, Chen Wu, and in SPA 2005. And they show how to transform the graph into a binary search tree of depth O of log n in D plus log n rounds and O of nd plus log n messages, where D is the maximum degree. And although they do a binary tree, this O of log n depth binary tree can be easily transformed into other topologies such as expander, butterfly, or hypercube. And this protocol, similar to our model, uses gossip-based communication. And of course, all the protocols that you're going to see uses this peer-to-peer thing. That's what allows it to reconfigure, add new edges, and drop existing edges. So in gossip, each node can only send a message to one neighbor per round, and that's why this communication is very efficient. So it's very lightweight and efficient, since only one message is allowed per node per round. Another work somewhat recently is by Gilbert, Pandurangan, Robinson, and Trahan, and they show that you can actually solve this problem. That means convert G into any target topology such as an expander, hypercube, or chord. But this takes poilog rounds and has message complexity of similar to the Angolin. It takes its message complexity is essentially theta tilde of m, where tilde is hiding poilog factors, poilog n factors. This is not the gossip model. So here it is a normal distributed model where a node can send messages to all of its neighbors in one step. And a couple of years back, there was a paper by Gote, Einenthal, Scheidler, and Werthmann in POTSI 2021, where they show that you can solve this problem, specifically convert G into a log n degree expander in log n rounds, which is optimal. But this algorithm takes again data at almost linear in M messages. And the important thing to note is, although all these algorithms are pretty fast, except Anglin, because it uses gossip based, and so it could be small if D is large. It could be slow, but all these algorithms take theta M messages, essentially theta tilde M messages. So this looks unavoidable because it seems that you have to you have to communicate over essentially almost all the edges of the graph. But however, Gotte et al., they raised this following question: can we design a fast overlay construction protocol that is significantly communication efficient? That means that takes sublinear number of messages, sublinear in M, or even O tilde n messages. That means about O n pi log n messages. So in this paper, our main result is that we answer this question in the positive and show that by showing a distributed protocol for this problem that takes log n rounds and O tilde n messages. And this is the first protocol that can solve overlay, that can construct an overlay in sublinear number of messages. And one reason for the efficiency of the protocol is that it's based on gossip-based communication. This gossip-based communication is not only like efficient, lightweight, and it's also robust and very easy to implement. And as a consequence of this result, I won't talk about this too much, but as a consequence of this main result is that you can solve fundamental distributed computing problems such as broadcast, redirection, minimum spanning tree, etc., very efficiently in this, what we call as the P2P gossip model. That means you have P2P power as well as the gossip thing. I mean, you can reconfigure, you can change the topology by adding and dropping edges, as well as you are only restricted to gossip-based model. Okay, so you can solve all these problems in essentially log rounds and O tilde n messages. So that's our main result. So before we talk a little bit about the algorithm and the main high-level ideas of the result, let's focus a little bit more precisely on the model. So this P2P gossip model, this is the same model that is also used in the Anglin paper. So you're given a connected reconfigurable graph on n nodes and m edges, and each node has a unique ID. The ID has some logarithmic number of bits. And we assume the P2P facility. That means a node can directly communicate with the node if it knows the IP address or the ID of that node. And it can also add an edge, create an edge if it wants to that node. So we don't assume any, the important thing is we don't assume any global knowledge except probably knowledge of n. So a node initially has knowledge of only its own ID and the IDs of its neighbors. That's very important. So it's local knowledge. And the communication model is a gossip-based synchronous model in which in each round we assume that a node can contact a neighbor and it can send a message of small size, log n bits to the contacted node, and it receives a reply. And each node after receiving any messages performs some local computation, maybe change some edges incident on it, and that's it. So this keeps happening. So the graph topology can keep evolving. So this is the P2P gossip model. So the rest of the talk is I'm going to give you a high-level overview of the algorithm, a little bit of analysis, and I'm going to mention two interesting primitives that can be of independent interest. One is reducing degree in an expander graph, basically from log n to a constant. And the second is computing graph sketches using gossip. So this is the high-level overview. So the input is some arbitrary graph, connected graph, and the goal is to transform this graph into an expander graph. And this high-level strategy is very simple and conceptually easy to understand. It's basically, for people who know distributed algorithms, this is basically, you can think of it as a variant of the classic Gallagher-Umlatt-Spira algorithm for minimum spanning tree, in the sense that it involves forming clusters and merging clusters. So initially, each node is its own cluster. So basically, There are n clusters to start with, and we do like O of log n phases, and in each phase we merge a constant fraction of the clusters. And the guarantee that we have is we always maintain two properties in every phase for each cluster. This is the invariant for every cluster. So every node in the cluster is constant degree, and every cluster is an expander with constant conductance. So if you maintain this at the end, we'll have only one cluster, and it will have bounded degree, and it will be an expander since it will have constant conductance. So of course, this is initially trivially true because each node is its own cluster. And the main strategy is to show how to maintain this invariant in every phase. Okay. So in the next slide, I'm going to talk a little bit about graph sketching, which is important to maintain these two properties. And then we'll talk a little bit more about a little bit more details on each phase. So the high level of idea of graph sketching, this is just a recall of graph sketching. So the main application of graph sketching is once I have a cluster, I want to find outgoing edge, because that's what happens when you use like a GHS or Boruca algorithm for finding a minimum spanning tree. So you want to find an outgoing edge of a cluster so that you can merge clusters. So here, if you do it naively, this will take O of M messages, and that's what GHS and algorithms do. So instead, we want to use sketches so that we use subline. We use only O tilde N messages per phase. So let's recall the incidence vector of a node. So for every possible edge, so if an edge for a node, for every possible edge UV, if the edge exists, we give a +1, and if the ID of U is greater than IDV, otherwise we give a -1. If an edge does not exist, we give a value of 0, right? And for a cluster S, that means for a subset of nodes S in the cluster, so the IG of the cluster is simply the sum of the IGs of the incidence vectors of all the nodes in that cluster. And it's very easy to see that this incidence vector, the summation of the incident vectors of the individual nodes in the cluster, which is equal to the incidence vector of the cluster. If you will the ones and the non-zero entries in this incidence vector simply correspond to all the outgoing edges. That means all the edges that leave the cluster. So this is good because then I can sample one edge from this, just take one edge from this set of non-zero entries. But the point is, this IGU, even IGU, this incident vector is large. It has n choose two entries because there's an entry for every edge in this incidence vector. So the classic, now the well-known solution is to use a sketch function to compress this incidence vector from n choose 2 bits to basically log n bits. And so I won't go into this, but this is now well known is that you can construct linear sketches from using essentially log square and true random bits. So you don't need too much randomness, just using log square and random bits, you can construct a sketch. And then once you have the sketch, so each instance now, so basically a sketch is a much compressed representation of the incidence vector of n choose 2 bits. So each node constructs its sketch using its adjacency list and this log square and two random bits. And now you have to add the sketch vectors, just like we added IGS, we add the sketch vectors. And now of course the sketch vectors are only log n bits, because each sketch vector each sketch vector of a node is log n bits, and they're simply adding these sketch vectors component wise. And the important thing is that you can sample an outgoing edge from this log n size instance vector and this sampling will give a outgoing edge with constant probability. So this is so I won't go into the details. This is well understood in the sketch literature. So now let's see how this is crucially used, where we use this in our overlay construction algorithm. So as I told you, the overlay construction algorithm is quite simple. It basically consists of phases, basically log n phases. So I just have to tell you how to do one phase correctly. So in each phase, we maintain two properties. So, and what are the two properties? Each node in every cluster has constant degree, and each cluster is expanded with constant conductance. Again, this is trivially true in the beginning because each node is a cluster by itself. So there are three steps in a phase. So in step one, the step one is basically preparing so the step one is to prepare the setting for finding an outgoing edge of the cluster. So how do we do this? We first do rumor spreading. So basically we so all nodes will find the minimum ID. Let's say they learn the minimum ID in the cluster. And this is just to figure out, because all nodes need to have the same log square and random bit string. So the minimum ID will now broadcast, again, we'll do this by gossip actually. So it will gossip log square and random bits. And so all nodes in the cluster will learn the same log square and random bit string. And now step two is the place where we are going to use sketching. Okay, so now each cluster I'll talk about this procedure called aggregate sketch vector, where we have to do this in a distributed fashion, this aggregation. And using this aggregating sketch vector, using this aggregation procedure, we can aggregate all the sketch vectors and sample an intercluster edge, just like I mentioned in the previous slide. And the point is, when I sample these edges, outgoing edges, many edges can go to the same node, and thus some nodes degree can blow up. Okay, but by using the power of P2P, we do a simple degree reduction so that we sparsify. If a node has high degree, we sparsify it. This can be done quite easily. For example, by putting a sparse. This can happen if you have a star, a lot of nodes connecting to one node, and you sparsify that star by, let's say, by cycle, where every node has degree 2. Okay, so that trick we have to do. And once we have these clusters with outgoing, this connection of, once you have these clusters plus these outgoing edges, this is no longer an expander. Although the clusters before the beginning of at the start of the phase, they were expanders, but once you merge clusters, they are not expanders. And here, this is why we do step 3, which is a nice procedure due to Gote, Inenthal, Scheidler, and Werthmann. They show this procedure in their paper, where they show how to take uh, like a bounded degree cluster to a log, and they convert it into a log and regular expander with constant conductance. And one thing is, again, it's slightly, because initially we had our clusters at constant degree, that was invariant. But by doing this, we got an expander, but its degree slightly increased. So we cannot allow this to happen in every phase, because then the degree will keep going up. I mean, log n will become log square and so on and so on. So we have to reduce the cluster. So this is where we do the degree reduction. So we have a procedure that reduces the degree. That means it takes an expander of log n degree and makes it into a constant degree expander with again a fixed conductance, constant conductance. Okay, so that's basically the 3 steps. So at the end of 3 steps, we have the invariant again. The clusters are merged, and we'll show that with constant probability, a constant fraction of clusters would have merged. So the number of clusters are reducing by a constant factor. And again, the invariant is holds. That means each cluster has constant degree. Every node in the cluster has constant degree, and each cluster is an expander. So let me talk about these 2 primitives. One is this aggregate sketch vector using gossip. So basically we have a constant. So this procedure is executed in a constant degree expander. So the idea is, everybody has constructed, because we have done the rumor spreading step, so everybody has the same log square and random bit string. And now every node has computed a sketch function. And now the main thing to do is to aggregate these sketch vectors. And this has to be done in a distributed way. And the main idea is, I won't go into the details, is to adapt push sum, which is a well-known aggregating algorithm. It's a way to aggregate if your nodes are connected, let's say by a complete network, and you want to aggregate the values using gossip, then this push sum is a nice protocol that was given by Kempi, Dobra, and Gerke in Fox 2003. And we have to adapt this because we don't have a complete graph. So their protocol works for a complete graph. So, but we have to adapt this to work in an expander. So that's not very difficult. And also the more important thing is their push sum just aggregates values. Here we have to aggregate sketch vectors, which are vectors that have both positive and negative values. So you have to aggregate them so that you are able to retrieve you are able to compute the aggregated sketch vector with enough accuracy. So that's the main challenge here, and it's not difficult, but that's what we do here. So the second primitive I want to talk about is degree reduction expanders. So again, we are given the goal is used in step 3 of each phase. So because we again bring it back, we get by the Gote procedure, we get a high conductance log and regular expander. And we run this degree reduction procedure to sparsify this expander graph into a constant degree graph with some fixed conductance, constant conductance. And this we show that this can be done in log cubed n rounds and n log cubed n messages. And the main idea is using random walks. So we use random walks, and the nice thing is random walks can be easily implemented using gossip because it's lightweight and can be easily simulated with essentially only like logarithmics slowdown using gossip. So using random walks and rapid mixing and the rapid mixing expanders, we show that given this more denser expander, I can sparsify this. Okay. So finally we come to the analysis of the algorithm. So to putting all this together, we show that the overlay construction problem can be solved with high probability in essentially like in basically polylog, but we are not very careful with the polylog. So basically we get log to the 5 n rounds and O tilde n messages. So let's first look at correctness. I sort of informally explained it, but basically we start with clusters of constant degree, constant conductance expanders, and each cluster samples an intercluster edge with constant probability, and we can show that this results in a constant fraction of clusters merging with at least constant probability. And the resulting clusters, we ensure the invariant that they are still constant degree clusters and they have constant conductance. And so after log n phases, you end up with one cluster which is constant degree and constant conductance with high probability. So the time and message complexity is that for log n phases, rumor spreading is just gossiping in an expander, which is log n rounds, and aggregating sketch vector. I didn't go into the details, but if you implement the push sum algorithm, this will take O log to the 4 n rounds, and this degree reduction, which happens when many clusters, many outgoing edges, cluster edges, if they go to the same node, you have to do this simple sparsification that takes constant rounds. And this create expander procedure by Gotex et al. Takes log square and rounds. And degree reduction, I just showed you, we have to apply degree reduction so that we again flatten we bring the degree back to constant. So that takes log cubed n rounds. So the costliest step is the sketch vector. So that takes log to the 4 n rounds. And that is done for log n phases. So log to the 5 n rounds. And message complexity is simply n to the basically O of n to the log n to the 5 rounds. So O tilde n message complexity. So to conclude, so we presented an overlay construction protocol. So it's a very well studied problem for the last maybe 20 years now, especially with the rise of peer-to-peer and overlay networks. And we showed that so the main takeaway is that we can create an peer-to-peer network, an expander network from any arbitrary connected graph in basically Poilog rounds and O tilde n messages. So that means this is regardless of the number, even if the original graph is dense, if m is large, still it is O tilde n messages. So we also did some experiments to see how our protocol does in practice, and we ran our protocol on many different types of starting graphs, and they all converged quickly to an expander with constant conductance, with essentially best conductance possible after log and after actually had very few phases. And so a nice implication I didn't talk about this, that many fundamental problems like MST and broadcast and lead election can be solved in this model, in the P2P gossip. If you have P2P gossip, especially the P2P power, then you can solve this in O tilde 1 time and O tilde n messages. And this has implications to some complexity issues in distributed computing models. I mean, so we talk more about this in the paper. So as for future work, I think it'll be nice. I believe we can improve the round complexity to close to log square n. I don't know whether we can do it even below that, but maybe it's possible we can improve log to the 5n to log square n. That'll be nice to do. And more interesting is to handle churn, because actually peer-to-peer networks are not only reconfigurable, they are also dynamic. That means nodes leave and join. So the network is also changing. So can we adapt this protocol to deal with churn also? And the question is, can we solve other problems like in this model for like shortest paths? So we can do MST, for example, which is already slightly non-trivial, but it's explained in the paper. So can we do something like shortest paths? Thank you.